Hi, in this video we will introduce the notion of orthonormal basis. Well, let me start with the definition of orthonormal sets. So a set Q1, these are vectors Q2 up to K is called an orthonormal set of vectors if first of all it is an orthogonal set and the vectors Qi are normal vectors. Well, if I want to write these conditions, it means the first one means that when you dot product Qi to Qj, when I is not equal to j, you get 0. That's orthogonal set definition. But the second condition means that the length of each one of these guys, these vectors, is 1 for all I from 1 to k. Well, we can rewrite this condition of Qi, the length of Qi being equal to 1. While the length of a Qi is 1, it means that its square is 1, and length square is nothing but dot producting the vector to itself. And this means that this is true for all k's. Well, if you look at these two conditions, now it seems that you just dot producting all the vector to themselves and everyone else. And there are two cases. That's why orthonormal sets, sometimes you write the conditions like this. Orthonormal set conditions can be written this way. Qi dot Qj is equal to 0 if I is not equal to j, and it is equal to 1 when I is equal to j. So we are checking all the possible pairs, not just distinct ones, all of them. If the vector is considered with itself, then the dot product must be 1, otherwise it should be 0. Well, moreover, if an orthonormal set is a basis, we call it an orthonormal basis. It's orthogonal, it's normal, the vectors are normal, and it forms a basis. Well, the most famous example of orthonormal basis is the standard basis of Rn. So the standard basis, which was what we denoted by E1 up to En of Rn, is an orthonormal basis for Rn. Well, checking the conditions are not difficult. Well, we already checked the orthogonality. Remember, I have to add one more condition. Ei dot Ei, so you have all zeros but the ith component. So here we are just multiplying those ones together. You get 1, everything else is 0. So this will be 1, and Ei dot Ej If I is not equal to j, it's going to be 0. Okay. Well, finding an orthonormal set, the main part will be based on the orthogonality part. And we can always turn or construct an orthonormal set out of an orthogonal set. So let me just write this, how to construct an orthonormal set out of an orthogonal set of vectors. Well, you see, if I have vectors v1 up to vk, which are orthogonal, and we have to make sure that vi's are not 0, and vi's are not 0. Then I can make a new set q1 up to qk, which is orthonormal. How do we do that? Well, I already know that v1 up to vk are orthogonal, so any non-zero multiple of them also will form an orthonormal basis. Now I have to make sure that they have length 1. Well, this is what we call normalizing or normalize vi's. What do? We divide or multiply every vector by inverse of its length. This was what we have been doing for a long time. So this is what we will call qi, and well, these guys QI's are orthonormal base. So basically you have orthogonal set of non-zeros. To turn it into orthonormal set, you just normalize all the vectors. Okay, so let's do an example here. Paste. We have an orthogonal basis, and we are asked to find an orthonormal basis or construct an orthonormal basis out of that. So each one of these guys, we have to normalize it. Normalize. So q1 is going to be 1 over length of the first one, which is square root of 1 squared plus 2 squared plus negative 1 squared times the first one, 1, 2, negative 1. And from there, you see that it is 1 over root of, this is 6, 2 over root 6, and negative 1 over root 6. Q2 is 1 over root negative 1 squared plus 1 squared plus 1 squared. And 1, negative 1, 1, 1. So from there we have negative 1 over root 3, 1 over root 3, and 1 over root 3. Okay? And Q3 is 1 over root 3 squared plus 0 squared plus 3 squared times 303, which will give us 3 over root 18, 0 over root 18, and 3 over root 18. Well, indeed, this, guys, you can simplify a little bit and write it 1 over root 2, 0, 1 over root 2. So the orthonormal basis, we construct orthonormal basis is now 1 over root 6, 2 over root 6, and negative 1 over root 6. Negative 1 over root 3, 1 over root 3, 1 over root 3. And 1 over root 2, 0, 1 over root 2. Now that I have an orthonormal basis, I can look for example, coordinates of any given vector in that basis. Yes, remember that when we have an orthogonal vector as basis, we can write any vector as linear combinations of those ones. Well, so far it means it's a basis. But when it is orthogonal, we have these coefficients given this way. Yeah. And for V3, now, well, if I have an orthonormal basis, not only they're orthogonal, but also the dot product of everything to itself is 1. So if we're working with orthonormal basis, the denominators of these guys are going to be 1. And what we will get this time, well, if this is orthonormal basis, we don't need to be worried about the denominator because all the denominators are going to be 1. And what we have is q1 dot w, q2 dot w, and q3 dot w. Note that these are constants and we just multiply them. Scalar multiplied to vector. Well, in this specific case, the w is 333, so we multiplied these guys to 333. We get, for the first one, dot product of 333 to q1. This will give me 3, 6, minus 3, so this will be 6 over root 6 of 1 over root 6, 2 over root 6, and negative 1 over root 6. That's the first coefficient. The second one, 333, so they will cancel. This will be 3 over root 3, negative 1 over root 3, 1 over root 3, and 1 over root 3. And for the last one, it will be 6 over root 2, and that is 1 over root 2, 0, 1 over root 2. As you see, in the case of orthonormal basis, finding the coordinates of a vector with respect to the basis is even easier. Let me write this thing. We already did the example and we showed why is that true. But let me write the statement now. If q1 up to qn is an orthonormal basis for Rn, then any vector W can be written as linear combinations of q1, q2 up to qn. The coefficients are just simply dot product of the corresponding vector from orthonormal basis to the same vector. So q2 dot w, this is a scalar multiply q2, and this will go to qn dot w. Well, we will work with orthonormal basis in more details when we study orthogonal matrices.